All right, that was cool. So we have an awesome panel here today to talk about what I think, started calling utility scale DERVS, but this idea of distributed energy systems that are gigantic, that are helping large industrial loads, in this case data centers, get up online. I think we're also here to talk about, though, those loads themselves being DERVS, which is really interesting. Before we get into it, I want you all to know who we're hanging out here with today. We have an amazing panel. I'll let each person introduce themselves, starting here with Hallie.
Hi, everyone. Really excited to be here. My name is Hallie Carrao. I sit on a team at Google called the Advanced Energy Team. Our team focuses on emerging energy solutions to support Google's clean energy goals, so specifically 24/7 carbon-free energy by 2030. It's split into two sides. One is focused on data and software solutions, technology partnerships, then the other is focused on advanced technologies, hardware solutions, so think nuclear, long-duration energy storage, geothermal. I sit on the data and software solutions side, and I've been at Google for 6 years now. When I started, I was doing energy analytics for our 24/7 carbon-free energy goals, so measuring, tracking, forecasting, building tools for 24/7 carbon-free energy. And just in the past year, I've switched focuses to really focus on this demand-side flexibility concept for data centers. So excited to be here today to talk about that and to share more about how Google thinks about it.
Wait, data centers can be flexible? I thought they were 100% capacity factor. Interesting. All right, Sean?
Hey, I'm Sean Jones. I'm on the Tesla Megapack team, and I am our market development leader for the data center segment amongst Megapack. We're seeing a lot of interest in having Megapacks on site at data centers, both to help deal with kind of AI power jitter and improve power quality for all of us on the grid, to help enable that flexibility that Hallie was talking about, lower cost and accelerate speed to power. Excited to be here.
And I'm told Sean worked on the Memphis XAI project that everyone's very interested in, has been interested in seeing the uses for batteries there.
Sounds good.
Tyler.
Hi, everyone. Great to be with you. Thanks for coming out. I'm a fellow at Duke University, also doing a PhD there. I have a background in electricity market forecasting, and then developed solar and storage for about 5 years. And a lot of my research is focused on large generator interconnection and how to accelerate it via flexible interconnection, and then now more focused on large load interconnection. I will have a change in status and a new role in a few weeks we'll be announcing, but excited to have this conversation.
Amazing. Yeah, Tyler's obviously impacted the conversation on data centers quite a bit. Lastly, we have Vic Shao. Vic, tell us about yourself.
Hey guys, Vic Shao. I run a little project development company called DC Grid. We power data centers as well as EV charging sites completely off grid using local generation, solar, storage, natural gas, and good to be with all of you today.
And Vic's being humble. He's the serial entrepreneur in the space who has a pretty high batting average. All right, so I want to start by just stating the key question that I'm trying to answer today, the thing I want to come out of this feeling like I have a better sense of, which is I want to know if there's any way at all to scale the compute and then therefore the power we need for that compute to meet the AI bull case in a manner that doesn't include the majority of data centers having DERs or being DERs. That's what I'm interrogating today, and I think we have an amazing group of 4 people to do that, but just keep that in your minds for the rest of this conversation. That's where this is headed. And I'll come back to it at the end and see what we all think. Let's start with the amount of energy that data centers need. I think in the electricity space, like the non-data center electricity space, there's a skepticism about this load growth actually happening, right? We all sort of grew up in an environment where there really wasn't much of any. We also know interconnection queues are a bit of a game, so is some of this fake? There's a general skepticism. So I really want to understand, do we actually need all this energy? And I'll just kind of state as the moderator, I think we might, right? So I want to see what this group says, but there's certain dynamics, right? where training models uses a lot of energy. We have like test time compute and scaling laws. And then there's also these use cases, right? Where like a chatbot uses this amount of energy, an image generator uses this amount, making a video is this amount, and deep research is even more. And basically, like the dynamic I see altogether is more energy equals more intelligence. And I think intelligence is pretty valuable. Yet, none of us really know if Sam Altman, for example, saying he wants 250 gigawatts not too far from now is realistic or absurd. So Tyler, I wanted to start with you. You're, I think, like a really great energy forecaster. Before you were doing, your PhD at Duke, you were in like the world of energy consulting, et cetera. What do you think of this? Does this feel real?
Everything's moving so fast, so I think it's really hard to have a solid forecast right now. So I'll say, though, I'm a little biased because I use this as a research tool, and I've saved thousands of hours just from the standpoint of like Python coding, and I love more and more chain of reasoning and multi-agent systems to just get better and better answers to research questions. I feel like one of the questions, though, is like, is there going to be a really large market for that type of function? Like, do most people want to use AI in that way, just like really heavy chain of reason and multi-agent systems? And I'm not really sure, because I feel like a lot of the daily tasks that most people will use it for may be able to be done in a more local inferencing case, and even potentially even locally on your own phone. So I don't know. I think that's one of the big questions, is like, how much do the more intensive use cases have a large and long-term market?
Yeah, I do wonder if like there's some world where every company's like corpus of information is being churned through constantly by these by these LLMs, and so you have these sort of hugely intensive things happening just all the time, ubiquitously, is it all just happening on the device? I don't know. Hallie, you're at Google. What do you think?
I think that there is a clear trend upwards. We do anticipate that AI will be a large part of our own growth. And we've also seen that over the years, the digital economy has become a large part of the modern economy. And that digital economy the backbone of that has been our data centers. So we think that it's really important to focus on how do we address the challenge of the day, which is speed to power, speed to capacity in a sustainable and responsible way. So we're thinking about it from that lens, but we do think there will be significant growth.
Okay. Anybody else? Any other strong feelings?
Well, I'll give you a different perspective. Prior to doing data centers, I spent 9 years in energy storage. I spent 7 years in EV charging. Just drawing from my experience from the EV charging space, at the time that I sold my last company and moved on to DC Grid, I mean, I had 60 some odd live construction projects around the country. I was dealing with 20 different utilities. Every single one of them was a 3-year wait, at least, to get even a megawatt of power for an EV charging hub takes 3 years, pretty much anywhere in the country. So, I mean, I think I don't know if that's an answer to your question, but it's certainly a data point that there's definitely low growth.
Interesting, yeah. I mean, and the other thing I feel like is in the conversation on how much energy AI will actually use is there's this sort of thing being dangled out there that like maybe we're going to get a big efficiency breakthrough. Maybe the NVIDIA chip in 6 years from now is going to be like 5x more efficient, and the problem basically goes away, right? And I think there's been observations about cloud computing, back in the 2010s, and like power intensity, or rather efficiency or effectiveness increased over time. Does anyone have any views on that? Like, are we going to see like huge improvements in efficiency or more kind of incremental?
What's been interesting just to hear, right, is that we're now moving towards like megawatt scale racks. And so it's just becoming more and more dense. It'll become more and more power hungry. One good thing about that is that it's going to open up more space, potentially just physically on site at the data center, such that maybe you can fit more batteries. But the density and the power use just seems to be going up.
I'll also add, we are seeing trends already in these energy efficiency gains as it relates to AI hardware. At Google, our 7th generation TPU at this point is around 30 times more efficient than the cloud TPU we launched in 2018. I think NVIDIA also shares a couple other stats around the efficiency gains that they've had with their most recent GPU that they launched, Blackwell. So we're seeing that trend. I don't know how far it gets us, but there's definitely uncertainty there. But I do think it's a core part of how we stay competitive also in this industry.
I'll open up a big can of worms with this comment because the name of my company is DC Grid. It stands for direct current. So the can of worms is that as all of us know, data centers and computers run on ultimately direct current. EV chargers, the fast charging variety runs on direct current. And here's the rub. I mean, when you have a large battery system or solar system, it ultimately gets converted into AC that gets transmitted over transmission lines, distribution lines, then ultimately gets to the destination to serve the loads and another step of conversion in between. So ultimately you end up with an efficiency of, I don't know, best case 92%, Sean, would you agree? 92, 93% in that range? Whereas I think and the rest of it, by the way, that gets lost is in the form of heat. So when you're talking about a data center that's, I don't know, 100 megawatts, just for rough numbers, you're talking about 8 megawatts of heat that's generated, that's being wasted. I mean, it's pretty significant. And then you have to have built a big HVAC system to cool it all down again, of course, right? So I think there is going to be a change coming for the industry where you start to power these loads directly using direct current. So I think NVIDIA is advocating for 800 volts DC directly into the building, and I think that's kind of going to be the path forward. And efficiency gains is really one of the big reasons for doing it.
So you see efficiency opportunities in kind of the system architecture, the balance of system, all that stuff. Maybe the chips as well, but that's kind of where you're interested.
Yeah.
Sean, any last thoughts here?
I don't have a ton to add, Duncan. I'm not a computer scientist. I'm a power guy. So I don't know, are these forecasts true or not? As I reflect on it, the AI is doing incredible things. As Tyler said, it's making us more efficient at our work. It drives my car for me now, which I love. I think maybe it was even Google this week said hey, we made a cancer breakthrough with an AI. And I don't want to be, from the power sector, I want to make sure we aren't slowing down, reducing road fatalities or solving cancer. And so in my mindset from the power sector, it's how do we accelerate all of these kind of scientific advancements that we can while doing it in a no regrets manner in terms of the infrastructure that we deploy, and doing it in an environmentally sensible way as well.
Yeah.
I'll just stay on that really quick. We've already blown through the Turing test, right? It's just funny how we just surpassed it and there's no big news. I sort of think the new test is can an AI system win a Nobel Prize in the fundamental sciences?
Yeah.
I think that's the new bar, and I think that's one of the big questions. Can it do actual fundamental breakthrough work?
Okay, so maybe I'll just close out this particular topic with I think everyone's already asking, what if this infrastructure build-out's a bubble? And I don't think enough people are asking, what if it isn't, right? Because the challenge is enormous. And again, 250 gigawatts by 2033 for one company. I'm sure there's a little bit of flexing there, but that's pretty crazy. So let's move on to the sites themselves and how we're going to power them. Everybody now wants 1 gigawatt data centers. This is wild, right? A few years ago, people would talk about 100 megawatts as kind of the big data center. Now we want these 1 gigawatt clusters. There's not many examples of 1 gigawatt point source loads on grids, but they do exist, and they're aluminum smelters. There's something like 30 of them on Earth, I don't know, that are 1 gigawatt class. There's a handful of these things on Earth, and every single one of them has really kind of bespoke special setups with their utility, right? interesting flexibility agreements where they like ramp down the smelter at certain times, or they have captive power plants, they have pumped hydro. Basically, like you had to build the power system to accommodate them, not the other way around. And so this notion of we're going to have many, many 1 gigawatt point source loads, way more than 30, they're going to be all over Earth, everywhere, I think it's really challenging. And to me, it says there's no like status quo assumption for what's actually going to happen here, right? We're like in very uncharted territory. And so I guess what I'm interested in is how we can actually scale this, right? So I want to kind of go around the room and just hear, maybe from your perspective or like your stakeholders' perspective, like how are we actually going to accommodate? Do people actually feel confident that we can like actually accommodate these massive loads on the grid in a manner that looks anything like we've seen before? Or is the assumption within all of your organizations the future is very different?
I can start. And I want to start by taking a bit of a step back and think about the difference in the state that we're in right now versus the past number of decades where, as you mentioned, it's been fairly flat load growth. We're in a state right now where the primary constraint is power. It's our power supply. And for Google, that means we've had to shift our mindset when it comes to data center site selection to think about an energy-first mindset. So when we go before we sign any contracts, before we build anything, when we're thinking about a new site, we are evaluating what the impact will be on that local community, on the power system that we'll be operating on. And that has led us to focus on 3 main levers. The first one is speed, thinking about solutions that can scale and can scale quickly. The second is innovation, so thinking about we do need to bring new solutions to the table, not just on the technology side, but also from the perspective of rate design, business models. What can we bring to the table that can think about things in a new way and help meet this new challenge? And then the third is efficiency. We know that there are sticky points in our system today, slow processes, and how do we use this opportunity to build more for the grid and get rid of some of those barriers so that we can set the grid up for a future investment cycle that is better for everyone. So I know I didn't directly answer your question, but I think that it's really important to think about that context and how we're addressing the power needs today and how can we get more out of our existing system and also use this as an opportunity to invest in a under-invested grid to date.
Mm-hmm. Yeah, I imagine in any big org, it's difficult to like move on from there was a playbook we used for 10, 15, 20 years to like everything is different.
Yeah, and specifically also related to our clean energy goals, there's no playbook for how to do 24/7 carbon-free energy at this scale. We'll need to think creatively and bring new solutions to the table.
Yeah, any other thoughts here? Do you guys feel like your orgs see the status quo just kind of meeting the moment, or is something new coming?
I think, especially if you want to connect to the utility system, there's a lot of precedent of 1 gigawatt power plants. So I think we have, good historical context there. The question is, how do we do that really fast? And, in the US, we've created this long interconnection process where it could take like 7 years to get approval to build a power plant. And we're asking, how do we move much, much faster? And I think that'll be a really important thing for us to, look at so that we can enable these loads much quicker. And like candidly, Texas, you can build a power plant in 1 or 2 years. And so like the rest of the country should maybe look at that and say, is there something there that we should tease out and think about? So that's kind of one piece that I think is, promising, but something to look at. The other thing is you talk about these bigger and bigger point source loads. Power plants kind of have rules of the road of how they operate on the utility system. Loads historically have not. And we're seeing that shift a little bit about, as loads get to this mega, giga scale, what are the rules of the roads that they should follow so that they can be good actors on the grid? And I think those are like the 2 things where like, if we look at how do we, interconnect power plants and how do we do those processes faster, and then how do we make like sensible rules to remove some of these contingency events that we get stuck up on, I think, you can really accelerate the on-grid build out of data centers.
I think that's a really interesting point about yeah, these huge loads kind of like blur the line between like the system and the user. It's like all the system, and it all needs to be dealt with in some manner that actually works.
I think it's important to actually conceptualize what a gigawatt looks like. So we're sitting here in New York City. Con Edison has a peak summer load of, I think, about 12 gigawatts. Con Edison also publishes something called a load duration curve, and it's the number of hours in a given year, 8,760 hours in a year, how many gigawatts is in the distribution grid. And the answer is that in a given year, Con Edison spends exactly something like 20 hours at the 12 gigawatts level. It averages about 5 or 6 gigawatts, exactly sort of halfway number of hours. So, look, I mean, a gigawatt is a fifth of the average load of all 5 boroughs in New York City. If you just think about it, I mean, a gigawatt is just ginormous, right?
So it is
absolutely ginormous. And you were talking about for point dedicated consumption, you have to build very dedicated substations, transmission lines perhaps, high voltage distribution lines. It's highly, highly bespoke, dedicated infrastructure for just that one point load. And who pays for it? I mean, is it that data center operator? Does it get shared somehow? These are all big, important issues that
I think we need to just
out.
come out and say it like our entire system of like electricity regulation and law was not designed for this at all. And really basic assumptions now are being totally called into question, like duty to serve, cost of service. I highly recommend a paper called Allocating Scarcity that recently came out in the George Washington Law Review by Alexandra Klass, University of Michigan, and her colleague. And they really go down to these bedrock assumptions that we've had in the power sector now for over a century. And I mean, you look at what's happening in PJM right now. I mean, the entire capacity market might dissolve, or it's just calling this question like, are we just going to go back to cost of service? I mean, that's the largest electricity market in the U.S. So, and the other thing is, this is like a classic case of like an unstoppable force meets an immovable object, and the immovable object in this case is like how we do power system planning, and the fact that we build everything to your worst case peak under multiple contingency. And it's impossible to build out the system fast enough to accommodate this amount of load this quickly if that's the way you plan the system. So I think that's in part what's driving this push towards DERs, of course, and on-site generation. But I think we're going to have to develop a whole new way of doing power system planning. And as we know, our utilities, in part because of the way they're incentivized, they're not necessarily inclined to go to a different approach. So, I mean, I think this also just goes to all these questions around, cost of service, performance-based rate making, getting away from just CapEx incentive.
It sounds like there's just a whole new power system paradigm that's going to be created in the next decade.
One thing I would add to your original aluminum smelter comparison in the point that you had around each being a one-off solution to address it or more ad hoc and will that scale? One thing to also acknowledge is that data centers are not a homogeneous group. There's a lot of diversity even within data centers in terms of the ML use cases they'll serve, the types of customers they'll serve, their business model and their preferences. And therefore, I don't think it's going to be one solution, but I do think we'll need a suite of solutions. And the more we can kind of standardize that suite, at least as it relates to solving for different use cases, I think the better off we'll be in terms of scale.
Yeah, it actually has to be repeatable. I want to talk about on-site power a little bit. This notion of there's no status quo anymore, I think very much applies to this. I think if 3 years ago, any of us approached any data center developer and said, you're going to need on-site power to do this, whether it's all the power, some of the power, whatever, they would say, I would never do that. That's crazy. What a huge waste of time or reliability or whatever the problem is, too expensive. Whereas today, it's certainly not all data centers, but a lot of them are planning for on-site power. A lot of them. And I think it illustrates like how quickly expectations are changing. Maybe Sean, I could start with you. Like, is that just a Band-Aid though? Like, is it just hey, the grid's not performing well at interconnecting loads, but we're gonna solve that, so yeah, there's like a few years where this is gonna happen, and then we'll get back to normal, kind of? Or even in a world where we do interconnections well, is there some like fundamental techno-economics that says some of your power, or in certain strange cases, maybe all of your power, like you should make it yourself? I mean, I know you've worked on some of these projects here, and also worked on helping make them actually function, which is much harder said than done, or easier said than done. What do you think? Like, can we actually scale that approach, and does it have a place in the mix here?
Yeah, it's a really good question. I mean, I think the honest answer is the easy button for data centers historically was go to the transmission system, say, hey, I'd like my 100 megawatts. That will be in 9 months. Thank you very much. As we've gotten bigger and the system's gotten more congested, that's slowed down. So that kind of quality of service in some regions has reduced. And so now it kind of opens up, the whole area to competition. So now the electric transmission system is effectively getting competition from the natural gas transmission system.
Yeah.
Where people are saying, hey, can I go get natural gas and build a power plant on my site? And is that faster? Is that better quality service? And at the same time, people are exploring how can I do massive off-grid solar and storage facilities to power my data center as well. And so it's kind of like, I'd say there's more options being reviewed now, and there's more competition that's being looked at, and it's really fascinating. And it's all a game of speed to power and then long-term probably cost of if maybe natural gas is the fastest speed to power. Do I stay on natural gas? It probably depends on that cost. So that's the, I think my take on that, and it's fascinating to watch that play out and really fun.
But like maybe on the other side of it, do you find that those, perhaps like myself, who are like, yeah, we're just going to build all these off-grid, it'll be fine, are perhaps underestimating the challenges that come with actually operating a multi-hundred megawatt off-grid microgrid?
I think it's hard.
For these insanely volatile loads? Like, tell us a little bit about dealing with like a power system like that.
Yeah, and I think, in concept, it sounds easy. I want to build, a 500 megawatt off-grid power plant or something like that. And there's a lot of engineering complexity that goes into that. But then you throw the data center in the mix, and particularly an AI training data center, and those data centers, they can vary up to 90% of their power demand, at like really fast frequencies, 10, 20, 30 hertz even, like has been reported to some people in the industry. And it's kind of like you gave your child like too much candy or chocolate milk and gave them the world's most powerful light switch, and they're just going on off whenever they want. It really, especially like in the natural gas world, it will break that equipment very rapidly if you don't have a solution. So we've been using our batteries to help smooth that out and give a steady load profile to those natural gas generators. The other thing that I'd say is fascinating is as these natural gas plants have gotten bigger, not only are they using the batteries to smooth that out, but it's kind of started to embody almost what we see in ISO markets, where batteries are performing other services as well. So it's how do I use that battery to provide that spinning reserve, which in the ISO world, we call that an ancillary service. But that can reduce the fuel burn by 10 to 30% on site. So that's pretty cool. And then it's a capacity resource as well, where you can go and look at your ELCC curve or whatever on the utility system, but you can use that battery to manage your thermal derate of that on-site generator. And so it's like basically, by adding batteries to that system, not only can you deal with the AI loads, but you can like reduce the levelized cost of energy by like 20%. It's pretty cool.
It sounds like you're basically just building a utility system at that point. Like it's not just like some little microgrid anymore. You need like the full complexity and thoughtfulness of running a utility. Maybe not the full, but in that direction. Yeah.
Absolutely, yeah.
Vic, what's your experience been like? I know you're doing this as well.
I'm going to give you guys a company secret here from my last company. This is what you guys are paying for, by the way. So in my last company, we provided EV charging solutions to transit authorities, to a lot of fleets and things, and I had to provide temporary power solutions in a lot of the cases because the utilities just couldn't keep up with getting power, delivering power to the site. And here's a secret. I mean, we made all of our money on those temporary power projects. And it goes something like this. We think, we're going to get utility power in 2 years' time or in 3 years' time. So we only need you for that, stopgap measure. And so in our financial model, we kind of get the whole temporary system paid for in 18 months. Guess what? I left my company 5 years ago. We still have those temporary power solutions on site in many locations, even today, 5 years later. And why is that? A lot of the times the utilities just take longer. They just do. They give away a distribution transformer to somebody else instead of to the site that they had promised us that they were going to deliver it to. Shit happens. Anyway, we continue to provide power to those chargers on a temporary basis, and the customer is paying, in many cases through the nose. But hey, they still need it because otherwise their buses won't run. So I think the same thing will happen here in data center space, honestly.
I was just going to say, one thing that's remarkable, right, is like the U.S. natural gas combined cycle fleet, right, operates at like less than 60% capacity factor. So like there's so much energy in the system, and yet we're going to go and sort of build fully redundant, like behind the meter power systems, which is great business opportunity, by the way. But like there is a fundamental like resource inefficiency there, and partly it's a result of what we were just talking about earlier, just like this immovable force kind of meeting this, or an unstoppable force meeting the immovable object. So I think this is going to like have to push towards different planning practices and interconnection practices. But I think there are at least two questions on my mind right now. One is most of this going to be a sort of bridge power solution such that it sort of goes away or is only used for a small number of hours in the year for on-peak purposes once the grid connection is complete? And I think the second is like, are batteries going to compete against thermal on-site options? And I think that's like one of the big questions right now. I was just talking with some Wall Street guys 2 days ago, and they're like super excited about reciprocating engines. And there are all these new market entrants now supplying them, and they're achieving efficiencies they didn't think they could. And we haven't heard a lot of like battery storage deals announced. I know they're coming. Sean could talk about that. We've heard like, Iron Mountain Data Centers has their like 2-hour battery they're putting in front of the meter on their New Jersey center. They're doing one in Virginia. There are other deals happening that just like hasn't yet achieved full scale. So I think this is like going to call the question. Like, can batteries really compete in this kind of service option, or like is thermal going to be the primary power source?
Yeah, and I'll add, from Google's perspective, our strong preference is to look at solutions that, for a data center that is going to be grid connected, let's look at solutions that are going to be grid connected as well, front of the meter. And a big reason for that is reliability, thinking about cost effectiveness, and then also business flexibility in the longer term. If we are seeing these types of solutions as a bridge, our preference at this point in time is how do we use, I'll segue for you, flexibility to be that bridge potentially instead of some of the behind the meter or on-site natural gas.
Yeah, okay, interesting. I think it's a good time to transition to more like grid-tied flexibility type stuff. Why don't we just kick it off with you, Tyler? Like, is flexibility happening, right? Is the flexibility for faster interconnection thing happening? Obviously, nothing happens in a day in our space, but is there momentum?
Yeah, what's been mind-blowing that's been revealed over the past 8 months is that like we don't have quasi-firm or non-firm transmission service options for loads that want them. And that's been revealed in the PJM co-location docket and all around the country. And so, that's why, like, to the great credit of Southwest Power Pool, like, super innovative team there, by the way. If we could just clone them and like put them in every other transmission provider, maybe we'd have a chance at this. But they're moving forward with a non-firm transmission service here. They call it CHILLS, and they also have their co-located or electrically proximate.
Wait, what do they call it?
CHILLS. It stands for Conditional High Impact Large Load Service.
That's chill.
Yeah, it is. It's pretty based. Yeah, and they have HILGA, which is like for electrically proximate, co-located loads and gens. So I think, like, at minimum, we should provide those options everywhere. Right now, because of just like the total cluster that is PJM, it seems like something's going to move in that direction. But as you know, like the notion that in a year you would like get any new service tiers on the bulk power system is like crazy. It used to be like a 5-year cycle, and you'd have like multiple years of stakeholder process and like a 2-year-long regulatory docket in front of FERC. But it is moving. I just think one of the questions is like, is it just going to be this like bridge power solution with thermal options, or can we get some more innovative practices there with battery storage and some compute flex? And Google, I think, has been a real leader and trying to offer that as a service. But there's also a lot to come. Like we're going to learn a ton, I think, from Verus. I mean, they are, as you all know, like many veterans of the hyperscalers. They are committed to 4-hour lithium-ion battery storage. They'll be announcing groundbreaking in the next few months, at least on 1 or 2 targeted in service for 2027. And I think that's going to be like a key sort of test as to whether we can see some different options here.
And I totally agree with Tyler. The chills, which will get used on the hottest days of the year, great progress there. Dominion has their Cap Flex program, really similar kind of concept where, hey, in Data Center Alley, if you can be flexible for 2 hours at a time, about 50 days of the year, I'll give you more power today. And then PG&E has a similar program called Flex Connect that we've used for a lot of our EV chargers, so they don't get stuck in off-grid mode like Vic was talking about. And it's all about how do you bring a little bit of flexibility to the system, and it's usually between 2 and 4 hours in summer afternoons. And so, Tyler was saying, can batteries do that, or do I need thermal generation? Like a battery today, you can get roughly 12 hours of battery for the same cost as like the natural gas generators you're seeing today, because natural gas turbines have gotten so expensive and battery costs have just come down a lot. So I think there's a lot of opportunity with batteries. I would say, and hopefully there's some regulators in the room, be thoughtful about how you structure these flexible connection programs so that all these kind of various technologies can be considered. A lot of them today, they say, hey, you can sign up for this and I'll give you power, but no guarantee I'll ever give you power. And in practicality, they're in the business of selling power, so like they don't want to never give you power, but that's how the contract reads, and to underwrite that technically, it really kind of limits your solution set there. So that would be my feedback to kind of the regulatory audience for these programs is let's develop them, and then let's think about what is the reasonable boxing in of the problem statement that I need to help accelerate all these loads.
I want to tee you up, Hallie, to talk, because you just released a really important study on this topic and you put out some position statements.
Yeah, I'll first talk about, over the summer, Google announced 2 new contracts that incorporate demand response and flexibility. And as mentioned, the primary driver of those is speed to power. It's not an economic signal that we're responding to. And what our challenge that we've come across is that a lot of the incentives often aren't aligned when it comes to DR programs. And what I mean by that is it is very expensive to disrupt workloads. Each workload is going to have, even if it's an ML workload, it might have different varying levels of flexibility. I don't think flexibility will ever be a solution that can be held across all workloads, so it can't be something that's mandatory and we can't ramp down 100%, but we can provide some flexibility. It just needs to be aligned with also the data center long-term planning process. And in order to be aligned with that planning process, both on the utility side and the data center side, there needs to be, I think what Tyler called quasi-firm service, so better understanding the bounds of what that flexibility entails. It can't be uncapped, it can't be called on frequently, but can we create something that is called on infrequently in emergency situations, that has a bounded number of hours per year, that also solves for system resource adequacy needs? And the research that Tyler was referring to that Google sponsored, that E3 led in SPP, found that with an average, I think, of 10 hours per year, you can achieve effective load carrying capability, or ELCC values, on par with thermal resources, both in the winter and the summer, where the winter season is the longer peak, so you might need a longer duration. I think we studied 10 hours, and then the summer peak is more that 4 or 6 hour need. So I mentioned that to say that DR can and should be part of longer term planning processes, but we also need to work on aligning incentives to support those programs. And like I said, because data centers are diverse, that might need to look different for different data centers or different types of DERs even. There's also the offsite flexibility option that we want to pursue and develop as well, and we can talk more about that. But it needs to be incorporated in longer term planning. It needs to be something that has some bounds in order to enable businesses to be able to plan around it and assess the risk on their end as well.
Yeah. I just want to make sure we heard that. 10 hours on average a year of flex, giving ELCC at the level of thermal resources, like that is mind blowing. I mean, it's one study, it's SPP, like their caveats, but that is mind blowing, and it's like it just shows like how inefficient the planning process has been. That like we're not accounting for that yet, and you sort of ask, why is that the case? Like, why don't we have quasi-firm service tiers? I mean, go read Constellation's comments in the PJM colocation docket. I mean, what they basically say is like, the reason we don't have this is because the load-serving entities do not want it because it fundamentally challenges their core business model. Last thing I'll say, we need better language, like firm versus non-firm. I don't know, quasi-firm just sounds kind of silly, my own terminology, but the thing is like, firm is not firm. Firm is 1 in 10 planning. You're planning for one outage in 10 years, but it's actually worse than that. That's just the resource adequacy outages, let alone like the other source of outages. So like it's a spectrum, right, of firmness or non-firmness or flexibility, and we need better language. If people have proposals, maybe we can come up with something. But
I guess I feel like what I'm observing is that there's like to the system engineer, it makes perfect sense that flexibility in the interconnection process like clearly should be a part of it. To your point, we have like all these unutilized plants that we could just increase output from and then just make sure we deal with those 10 hours, that sort of thing. Yet it has to work its way through all of these institutions, and everybody has, stakeholder processes, which always means, it's going to be complicated. And so you have like a certain type of developers out there who are just saying, I don't want to deal with any of that, let's go right now. And there's a race. We're witnessing an AI race unfold. That kind of feels like the tension between these two solutions. I like both of them, by the way. But so I'm curious, though, when it comes to flexibility, it sounded like, Hallie, you were saying, like there's some amount of load that can be scheduled, and then while difficult, like there's certain things that can even be interrupted. But then there's some amount that cannot either. Like, do we think batteries are, in a world where flexibility for interconnection becomes very prominent, do we think batteries are going to do most of this job? Is like what I wonder. And like there's, for this value, but then all these data centers have UPSs anyway, all these data centers need to like black start backup generators anyway, these loads are really crazy, and even if you're connected to the grid, the utility's not happy about like sub-cycle load fluctuations. It kind of just feels like the end game is batteries everywhere. Like any power market that batteries are being developed anyway, you should put them at the data centers that are being developed. Is this, Hallie, Sean, both of you, like this feels like a layup to me. Like this has got to be what's going to happen, right?
I'll caveat first that the announcements that we made were very specific to our IT load dropping. So it wasn't incorporating anything. We weren't transferring load to diesel. We weren't transferring load to backup generation through batteries. We were looking at our IT workloads and what are the service level objectives or the reliability requirements of those IT workloads. And during these periods, again, planning for something that is very infrequent and is bounded, how do we either reroute, reschedule, or throttle those workloads such that we can drop load? So in the use cases that we've seen today, that has been what we focused on. Batteries, I think, will also be part of the solution, but it hasn't been part of, so far, of what we've announced.
Yeah.
Sean, you're a salesman. Give me something here.
Yeah. Well, I think for the IT loads, the equipment is phenomenally expensive if we put it in power terms. It's roughly $50 billion a gigawatt for those NVIDIA chips. And they have a 4 or 5 year lifetime. And so if you run the math, they depreciate at something like $2 a kilowatt hour. Whoa. That's like above the LMP cap. Like that's insanely expensive, electricity. And so interrupting those more than 10 hours a year, as Hallie said, is like, the dollars really tick up very rapidly. And it starts to say, okay, I don't want to interrupt my money-making equipment because A, just the depreciation's insane, and B, it's annoying. I want to go and transition it to something like an on-site resource like a battery. And we think there's a lot of potential there because, battery is kind of don't think about it, it's just there and it can do it. And then the battery, when it's not doing that kind of flexible load connection thing, can do so many other services for you meet the voltage ride-through requirements, move the AI loads around so they're flat, and help save you money on your power bill too, or help with the 24/7 green energy goals. So that's kind of our pitch and our view on it is a few hours of the year, maybe folks will want to turn off their servers, but probably won't. And then as it becomes many hours a year, it's like, okay, you definitely want to do it on a battery.
Like most of this, you think, comes from batteries?
I mean, I think you could do batteries, you could do your on-site thermal generation. Like, we should take a technology agnostic approach and look at all the options. I think from a air permitting and environmental goals and things like that perspective, I imagine a lot of the players will look at batteries for a wide variety of reasons.
I mean, part of this goes to the notion of the 5 nines uptime requirement and what type of extreme event you want to be able to ride through. And so if you're trying to plan for a 48-hour outage, it's hard to do that with batteries, obviously. And I mean, just to underscore how crazy it is, so if these are transmission connected loads, and you have anything more than a 12-hour outage, I mean, this is like a blackout event on the scale of like the largest blackouts that have ever occurred in US history that like led to the entire formation of NERC, right? These are like ultra low probability events. But like, of course, if you're trying to plan for the absolute worst case scenario always, it's hard to have it not lead you to a thermal solution. And I think one of the big questions in front of us is like, is the 5 nines uptime requirement going to basically just like hurdle us into just like deeper thermal commitment? Or like, is there gonna be a little bit of flexibility there and an evolution in the SLA and SLO structure that enable battery storage and other solutions to emerge? And again, I think Verus is trying to figure that out. It may still be, right? You put in the diesel, but the thing is, I mean, one of the big, by the way, it's a great series of paper that Enchanted Rock is putting out on diesel, and obviously they have a business interest to go after diesel, but there are a lot of good points in there, right? Like, it's actually quite dangerous, arguably, to store more than like 12 hours or maybe 20 hours of on-site diesel for like a multi-100 megawatt load. So I don't even know that like, and by the way, if you're in a level of a blackout of what we just talked about, like the notion that they're gonna send the diesel to like all the data centers instead of the hospitals and other critical loads, I just think is like, doesn't make sense.
Buy diesel fuel suppliers in Northern Virginia. I think that's a good idea.
You're making a case for efficiency, right? Which all of us in the room, I think, would agree that's the sane thing to do. But it's really not how the utilities are incentivized, is it? I mean, they are incentivized by deploying more stuff and making a rate-based return on that. So efficiency actually is not what the utilities want. So I think there's a bit of a
skeptical of the driver behind this. We could dive into that. We have 4 minutes left. I want to think about the future, right? Let's think about like terawatt scale compute. I'm not saying one site, but in aggregate, right? A really the top of the AI bull case, right? Where 15 years from now, there's 1 billion AI souls that help our lives, right? This sort of thing, right? And I've had the privilege to kind of sit in design reviews of some data centers now, not on the energy production side, but the data center itself. And these are extraordinarily complex sites, from utility transformer down to the rack. From a power distribution perspective, it's like a high art, right? There's like thousands of switches, hundreds of transformers, switchboards everywhere. It's like an immense amount of complexity to basically get electrical power into GPUs or TPUs or whatever. And I kind of want to just like ideate with you guys a little bit. Like, if we're going to get to terawatt scale stuff, like that just seems like we're just going to hit so many bottlenecks along the way. Like, there's not going to be enough switchboards, transformers, et cetera. And we're also simultaneously seeing kind of like the data center evolve into the quote AI factory, and some of this is like lingo and branding, but like there is some like difference here. Like Vic was talking about, we have like 800 volt DC architectures. I'm just curious, like, does anyone see any kind of radical simplification around the corner so this can actually become like gigantic, right? Because it's just hard for me to see Sam Altman getting 250 gigawatts by 2033 when there's like 6 engineering firms that know how to make a data center, right? Like they're so complicated. Vic, I'd like to start with you. Like, is there a radically simpler path that is like actually massively scalable that maybe in some amount of time that's actually how data centers will look?
Nuclear, maybe, but I don't think that's simple in and of itself. Look, I mean, I'm going to give you a very biased answer. Okay, so direct current, I fundamentally believe is the way to go to power all of this stuff. You don't need to sync. There are no phases that you have to sync. You know, it's very robust and resilient. The voltage and the power converters that exist. So it's just, I think that's ultimately where it's part of the solution. It's certainly not the entire solution.
I mean, and we just saw, we'll see if this takes off, but like Heron Power just released their DC product for data centers. Drew will be on another panel today, so maybe he could talk about that briefly. But in theory, this thing, you know, replaces the transformer, the switchgear, the protections, and just sends 800-volt DC through the building all the way down to the racks. This feels just like an example of the sort of thing we need to like actually scale this to massive levels. I don't know, Sean, if you have any views here on what's coming around the corner.
On the 800-volt DC thing, I'm going to be honest, I don't know. I think if you're a college PhD in electrical engineering, you should go and work on DC protection, it sounds like. And in DC, I mean, you know, direct current, not data center.
Yeah.
That's always been a really tricky subject. And that may be one of the main challenges of it. Yeah, I mean, I think the radical simplifications or the radical accelerants is, you know, Tyler's done great studies on how do we be flexible, and it's just continuing to think about how we partner in the energy system to help accelerate all our projects and get the, you know, fantastic AI work to accelerate our science moving would be my last thought.
Yeah, I'm not an expert to answer that question. I'm not informed enough, but I'll put a plug in for that last point around if data centers themselves can't be flexible. One other business model we're exploring is how do we partner with offsite DERs to build capacity on the system, customers that might have a lower value of lost load, for example, that can dispatch more frequently and use that as a tool in the toolkit to address flexibility if it's not on site at data centers.
Bringing your own grid capacity,
Yep.
Yeah, whether DERs, et cetera. Yeah, very cool. Maybe we just put these things in space at some point. That seems possible as well. Okay, so if we remember the question in the beginning, can we scale compute to meet the AI bull case and the energy required without most data centers either having DERs or being DERs? I want to just go around the room and hear from everybody. Hallie, what do you think?
I think it'll be very hard without that.
Okay.
This is not a straight yes or no.
No, that sounds like a yes.
My gut is it's probably most efficient for them to have some level of DER integration on site and really partner with that energy system to, you know, make it most cost effective and efficient.
Yeah, I mean, it seems inevitable. They're likely to have some form of on-site capacity, and I think the big question is like, is that going to be primarily thermal, or like can batteries and other options sort of compete? And a lot of open questions there. But also, like, how much of it needs to be on site versus distributed elsewhere on the system, and can you create a market for flexibility?
And to be clear in my question, I'm saying like, yeah, a flexible data center, I'm calling that a DER, basically. It is a DER on the system. Vic, what do you think?
It's essential. I mean, let's face it, we're not building enough transmission and distribution lines, and we won't, just period.
Vic's like, stupid question, of course. All right, well, that's all we got. Thanks, you guys. This was really fun.
Let's take a selfie, Dan. Can we? Let's take a selfie.